Hi, I'm Aurora Wild, and this is Astrophysics for Beginners. In this video, we will be covering black holes. For a refresher on anything that we've already covered, please check out videos about general relativity, Newtonian gravity, dark matter, and dark energy on my channel. In past videos, we have discussed how masses warp the spacetime continuum like this. Black holes, however, bend it more like this. They can be considered a rip in the spacetime continuum because spacetime does not exist in the very center. So let's look at a diagram of these amazing astronomical phenomena. The very center here is the black hole's singularity. A singularity is a point that is infinitely dense, and spacetime does not exist there. A singularity is infinitely small. Neither space nor time exists. We can think about why spacetime fails at these points by thinking about what masses experience while in a singularity. If you move from one side of a singularity to another, you haven't gone anywhere, so space does not exist. Space and time are so intricately linked that without space, time cannot exist. The way that we can gauge the space between 2 points is the time it takes us to get between them. Therefore, any mass that makes up a singularity does not experience space or time. These points, called singularities, are also seen elsewhere in astrophysics. The universe was born in a singularity at the Big Bang, and some theories predict the universe will end by condensing into a singularity. Let's go back to our diagram of how spacetime reacts to black holes. The singularity occurs about here. So when we talk about the surface of the black hole, we aren't talking about the singularity. We're talking about the area up here. The surface of a black hole is referred to as the event horizon, which is just the science way of saying the point of no return. Because once something crosses the event horizon, it's not coming back out ever. This is because the black hole has a lot of mass, so it has a very high gravitational pull. Once something crosses the event horizon, it would need to accelerate to a speed larger than the speed of light in order to escape. That's important because the speed of light is the speed limit of the universe, so nothing can travel faster than that. This means that black holes trap everything, including light, mass, and other forms of waves. So that's what makes a black hole black. No light is emitted from a black hole because all light is trapped by the gravitational pull, which is why we can't see them. So what happens outside of the event horizon? Is everything out of this range safe? Well, not quite. There's something called an accretion disk that rotates very quickly around a black hole. NASA produced this image of an accretion disk that may be helpful. Now, the accretion disk can be thought of kind of like a whirlpool around the black hole. It is made up of light, mass, and radiation that have not yet made it past the event horizon. Because the gravity of a black hole is so large, the gravity in this area is extremely strong, and most things on the accretion disk will end up going past the event horizon and becoming part of the black hole. Because the accretion disk is usually rotating at very high speeds, sometimes things can get shot off into space. We call these streams of mass and energy jets. So if we take this drill and funnel as an example, we can attach the funnel here to the tip of the drill, and you can imagine that this is the accretion disk of a black hole. Now when we put some salsa on the funnel, like so, this can represent mass, energy, and other waves that are stuck on your accretion disk. Jet propulsions are made up of the material from the accretion disk. So they're like clouds of X-rays, light, and other debris that get shot out of the black hole like a little laser into space occasionally. So if we come back to our drill and funnel analogy, we can see that this funnel is spinning, much like a black hole's accretion disk would in real life. And as it accelerates faster and faster, we can see that there is salsa that comes flying out of the top, much like a jet propulsion in real life. In this demonstration, there are different forces creating the result than we would see with a black hole. So in the demo, most of the salsa gets pulled down because of the gravitational force that it experiences towards the Earth while in the funnel. The bigger chunks that get thrown out because of the centripetal force of the moving drill. Whereas in a black hole, debris gets pulled inwards because of the gravitational pull of the black hole, whereas they get shot outwards because of magnetic fields in the accretion disk. A magnetic field is created when lots of charged particles are spinning very quickly, just like what happens on the accretion disk. So when there's enough of a charge rotating that quickly, it can create enough force to form a jet. And that's why we see jets with black holes. When an object is far enough away from the accretion disk, the black hole acts mostly like a very large star. Other planets, stars, and black holes can orbit around it without falling in. There are 3 types of black holes: stellar black holes, supermassive black holes, and intermediate black holes. Stellar black holes were the first black holes discovered. They are generally about the mass of 3 suns packed into the diameter of a city. These are formed because when large stars collapse, they become either a neutron star or a white dwarf. When those larger stars collapse, they can have enough mass to collapse all the way down to a singularity, creating a black hole. These black holes can be found throughout the universe with solar systems and planets orbiting them. When I first learned this, I thought that might mean eventually our sun could collapse into a black hole. You'll be glad to hear that our sun will not be massive enough to do that. The second type of black hole is a supermassive black hole. Supermassive black holes are about the diameter of our sun, but they are usually about the mass of 1,000,000 or 1,000,000,000 suns. These black holes largely determine the structure of our universe. Supermassive black holes have been found at the center of all galaxies and are thought to be necessary for galaxy formation. Our galaxy orbits a supermassive black hole called Sagittarius A. Scientists are unsure how these formed, but they have several ideas. They may form when large dust clouds collapse, or when lots of large stars near each other all collapse at the same time into one massive black hole. Other theories speculate that supermassive black holes come from dark matter collapsing. And if you want to learn more about dark matter, I have a video all about it on my channel. Some scientists say supermassive black holes originate from events like the Big Bang, causing them to live and die with the universe. The theory of intermediate black holes may also explain supermassive black holes, because intermediate black holes could merge until they became supermassive. The truth is, we don't really know how supermassive black holes are formed. Intermediate black holes would be a class of black holes between stellar black holes and supermassive black holes. These would be formed by several stellar black holes joining into one larger black hole, or several nearby stars collapsing into the same black hole. These have not been discovered, but scientists believe they exist because several intermediate black holes could join together to form a supermassive black hole. So now that we have a little bit of history for black holes, how do we detect them? Well, most strategies use some sort of observation of the accretion disk to make inferences about the black hole itself. The most obvious way to discover a black hole is based off of their gravitational pull. So when you see large amounts of solar systems, stars, and other planets orbiting an invisible center, there's usually a black hole there. We can measure the size of this following to determine the gravitational pull of the black hole, which can help us figure out how big the black hole is and how long it's been around. We can also take pictures of the accretion disk of a black hole to see a visual component of what these might look like. Another way that we can measure black holes is based off of the waves that they produce. Accretion disks produce X-rays, which we can measure. These X-rays can tell us a lot about the gravitational pull of a black hole and how quickly its accretion disk is spinning. Black holes can also be discovered based on their jet propulsions.
NASA's Chandra telescope detects X-rays emitted in large amounts throughout the universe, which means it picks up on jet propulsions from black holes, as well as other things like star explosions and clumps of galaxies.
Any seemingly random stream of debris hurtling through the universe at nearly the speed of light is likely from a black hole. Remember our drill and funnel analogy about what jet propulsions are? Well, when scientists find debris that interact like a jet propulsion, they can trace it back to find the black hole that it came from. And it can help us map new black holes that we previously didn't know about. Jet propulsions from black holes that we do know about are also helpful because it can tell us more about their size and what their gravitational pull is.
The future of black holes is very exciting. The Ligo Facility can measure waves produced when two black holes are orbiting around each other and they collide, forming one black hole. The LIGO facilities include two 4-kilometer-long arms that are connected at a 90-degree angle. The premise of the experiment is to shoot lasers into the junction of the arms where there is a mirror. Then the laser is recorded when it gets back to the end of the arm. Lasers are waves, and if the wave is in phase when it gets back, no major gravitational waves passed. But if the wave has experienced a phase shift, we know a gravitational wave distorted spacetime and caused the distance of the arm to either increase or decrease by minute amounts. These facilities are very exciting because they allow us to see gravitational events that occur in the cosmos that don't emit any visible light. This means that we can detect black holes that collide with each other and form into one. Major events that we would have never been able to see without LIGO.
The Event Horizon Telescope measures light, gamma rays, and X-rays that are emitted from black holes' accretion disks. Now, in order to image a black hole, a telescope would need to have a very large lens in order to get high enough resolution to see the black hole's silhouette. Now, because a telescope of this size cannot yet be built, this telescope accomplishes that by composing images from several different locations. So the effective width of the telescope is the distance from the telescope in Spain to the telescope in Antarctica, which is about the diameter of the Earth.
This is the photo that the EHT produced of the first ever imaged black hole. The Event Horizon Telescope took the very first image of a black hole by composing data from all of its 5 locations: Apex in Chile, IRAM in Spain, LMT in Mexico, SMT in Arizona, and SPT in the South Pole.
Stephen Hawking theorized that black holes themselves may produce some form of energy that we could measure. It's named Hawking radiation after him, and there's many studies going on now to see if this Hawking radiation is really there.
Black holes are truly an amazing phenomenon. I hope to see you for the next video in this series.